Picture this. You're holding a sugar cube in your hand. Now imagine that tiny cube weighs as much as every single human being on Earth combined. 6 billion people, compressed into something you could drop in your coffee. That's the mind-bending reality of neutron stars, the most extreme objects in our universe, where the very laws of physics are pushed to their breaking point. But here's what's going to blow your mind. We've been studying these cosmic monsters for decades, yet there's one mystery so profound, so fundamental, that it's forcing scientists to question everything we thought we knew about matter itself. And the answer to this mystery could rewrite the textbooks of physics forever. What I'm about to reveal isn't just another space curiosity. This is a puzzle that connects the smallest building blocks of reality to the most violent explosions in the cosmos. It involves stars that spin faster than your kitchen blender, magnetic fields that could erase every hard drive on Earth from thousands of miles away, and collisions so catastrophic they forge gold and platinum in the blink of an eye. The mystery I'm talking about has stumped Nobel Prize winners, challenged our most brilliant theoretical physicists, and opened doors to possibilities we never imagined. By the end of this journey, you'll understand why neutron stars might hold the key to unlocking dark matter, why some of them break the speed limit of physics, and how they're connected to the very gold in your jewelry. But first, let me take you inside the most violent birth in the universe. When a massive star, at least 8 times heavier than our Sun, reaches the end of its life, it doesn't go quietly into the night. For millions of years, this stellar giant has been fighting a cosmic battle between two titanic forces, gravity trying to crush it inward and nuclear fusion pushing outward, with the fury of billions of hydrogen bombs exploding every second. But eventually, the star runs out of fuel. In less than a second, gravity wins catastrophically. The core collapses so violently that protons and electrons are literally crushed together, forming neutrons. The collapse happens so fast that if you could watch it in slow motion, you'd see a core the size of Earth shrink to the size of Manhattan in the time it takes you to blink. The shockwave from this collapse rebounds outward, tearing the star apart in a supernova explosion so bright it can outshine an entire galaxy of 100 billion stars. But what's left behind is even more incredible. A neutron star, an object so dense that a teaspoon of its material would weigh as much as Mount Everest. Now, here's where things get truly bizarre. These neutron stars aren't just incredibly dense, they're spinning. And I don't mean slowly rotating like a planet. Some of these cosmic lighthouses are spinning over 700 times per second. That's faster than the blades of an industrial drill, faster than anything you can imagine. If Earth spun that fast, you'd be flung into space at thousands of miles per hour. But this is where our first mystery emerges. How is this even possible? How can something with the mass of our Sun, compressed into a sphere just 12 miles across, spin at such impossible speeds without tearing itself apart? The answer lies in the most exotic matter in the universe, matter so strange that it exists nowhere else, except possibly at the very moment of the Big Bang. You see, inside a neutron star, the normal rules of matter completely break down. In your body, in the ground beneath your feet, in every atom you've ever encountered, there's mostly empty space. The nucleus of an atom is like a marble in the center of a football stadium, with electrons orbiting somewhere in the nosebleed sections. But inside a neutron star, that empty space is gone. Matter is compressed so tightly that atoms can't exist anymore. It's like trying to squeeze 1,000 people into a phone booth, except the people are neutrons, and the phone booth is smaller than the period at the end of this sentence. Scientists call this neutron degeneracy pressure, and it's the only thing preventing these stars from collapsing into black holes. But here's what's keeping physicists awake at night. We have no idea what happens at the very center of these objects. The density there might be 5, 10, or even 15 times denser than an atomic nucleus. At those conditions, neutrons themselves might break apart into their constituent quarks, creating a state of matter that's never been seen before. This brings us to the heart of our mystery, the equation of state. Don't let the technical term fool you. This is actually a simple concept with mind-blowing implications. The equation of state is just a way of describing how matter behaves under different conditions of pressure and density. Water becomes ice when it's cold and steam when it's hot. That's its equation of state. But for neutron stars, figuring out this equation of state is like trying to solve a puzzle where half the pieces are missing and the other half might not even exist yet. And here's why this matters so much. The equation of state determines everything about a neutron star: its size, its maximum possible mass, how fast it can spin, and what exotic particles might exist in its core. Different theories predict wildly different possibilities. Some say the core is made of normal neutrons, just incredibly compressed. Others propose that the neutrons break down into quarks that flow like a liquid, creating what scientists call strange quark matter. Still others suggest that the pressure is so intense that it creates particles that don't exist anywhere else in the universe. Particles with names like hyperons and kaons that sound like they belong in a science fiction movie. But here's what makes this mystery so urgent. We're finally developing the technology to solve it. For the first time in human history, we can measure neutron stars with unprecedented precision. We can detect the ripples in space-time when they collide. We can measure their exact masses and sizes, and we can watch their surfaces cool over thousands of years. And what we're discovering is shocking. We've found neutron stars that are spinning so fast they should fly apart, yet somehow they hold together. We've detected others that are cooling far too quickly, suggesting that exotic processes are happening in their cores that we never predicted. We've witnessed collisions between these objects that created more gold than exists in all of Earth's oceans, forged in temperatures hotter than the center of the sun. But perhaps most intriguingly, we've discovered neutron stars that seem to break our theoretical models entirely. There's one spinning once every 6 hours, thousands of times slower than it should be able to maintain. There are others with magnetic fields so powerful they would be lethal to humans from thousands of miles away. Fields that can literally bend the shape of atoms. Each of these discoveries is like finding a new piece of the puzzle, but instead of making the picture clearer, they're revealing that the puzzle is far more complex than we ever imagined. And at the center of it all is a question that could revolutionize our understanding of reality itself. What is matter when it's pushed to its absolute limit? The answer to this question isn't just academic curiosity. Understanding neutron star interiors could unlock the secrets of dark matter, the mysterious substance that makes up most of the universe but has never been directly detected. It could reveal new states of matter that might one day be created in laboratories, leading to technologies we can't even imagine. It could explain how the heaviest elements in the universe are created and distributed, elements that are essential for planets like Earth and life as we know it. But here's what's truly mind-bending. Some scientists think neutron stars might be natural dark matter detectors, accumulating this mysterious substance in their cores over billions of years. If they're right, studying cold, old neutron stars could finally solve the dark matter mystery that has puzzled cosmologists for decades. Others believe that the extreme conditions inside neutron stars might create particles that violate the fundamental symmetries of physics, particles that could explain why our universe is made of matter instead of antimatter. Still others think that neutron star cores might contain microscopic black holes or even more exotic objects that challenge our understanding of space and time itself. The implications are staggering. We're not just studying distant objects in space, we're probing the fundamental nature of reality. We're asking questions about what matter is, how it behaves under impossible conditions, and what new physics might be waiting to be discovered. The answers could change everything. And here's the incredible part. We're on the verge of breakthrough discoveries. Advanced gravitational wave detectors are coming online that will detect neutron star collisions from across the observable universe. New telescopes are being built that can measure neutron star properties with unprecedented accuracy. Supercomputers are simulating these objects with ever-increasing realism, revealing details about their interiors that were unimaginable just a few years ago. In the coming years, we expect to map out the neutron star equation of state with precision, finally answering questions that have puzzled scientists for half a century. We'll discover whether quark matter exists in nature, whether neutron stars contain particles that have never been seen before, and whether these objects really do serve as cosmic laboratories for physics beyond our current understanding. But as we stand on the threshold of these discoveries, new mysteries keep emerging. Recent observations have revealed neutron stars that shouldn't exist according to our theories, others that are behaving in ways we never predicted, and collisions that are producing unexpected results. Each answer we find seems to raise 10 new questions, pushing the boundaries of human knowledge deeper into uncharted territory. The deepest mystery of neutron stars isn't just about these objects themselves, it's about the fundamental nature of matter, energy, space, and time. It's about understanding the universe at its most extreme limits and discovering what new physics awaits us there. And as we'll see, the answers might be stranger and more wonderful than we ever dared to imagine. What we've discovered in recent years has left even veteran astrophysicists speechless. Remember those neutron stars spinning at impossible speeds? Well, we've found one that breaks every rule we thought we understood. PSR J1748-2446 AID spins 716 times every single second. To put that in perspective, if you could somehow stand on its surface, you'd be moving at nearly 1/5 the speed of light. At those velocities, the star should disintegrate instantly, scattered across space like cosmic confetti. Yet there it is, spinning away, completely intact. How is this possible? The answer forces us to confront a terrifying possibility. Either our understanding of physics is fundamentally wrong, or neutron star matter is far more exotic than we ever imagined. The material holding this star together must be incredibly rigid, more structurally sound than any substance we've ever encountered. It's as if nature has discovered a form of matter that laughs in the face of physics. But if fast spinners confuse us, slow spinners absolutely baffle us. Deep in the constellation Centaurus, there's a neutron star that rotates once every 6.5 hours. This might not sound strange until you realize that most neutron stars spin hundreds of times per second. This cosmic oddball is rotating thousands of times slower than it should be able to maintain its lighthouse beam of radiation. How do you slow down a neutron star to such an extreme degree? The leading theory involves something called fallback accretion. Picture the supernova explosion that created this star. As the outer layers blast into space, some material might fall back onto the neutron star, but not in the way you'd expect. Instead of speeding up the star's rotation, this fallback material somehow acts like a cosmic brake, dragging against the neutron star's magnetic field lines and slowing its spin to this crawling pace. But here's what's truly unsettling. We don't know if this explanation is correct. This neutron star exists in a theoretical no man's land where our models break down completely. Its very existence suggests that neutron star formation and evolution are far more complex and unpredictable than we ever realized. Now, let me tell you about something that will make your head spin faster than any pulsar. Some neutron stars possess magnetic fields so powerful they defy comprehension. These objects, called magnetars, have magnetic fields a quadrillion times stronger than Earth's. To put this in perspective, a magnetar's magnetic field from halfway to the moon would erase every credit card, hard drive, and electronic device on our planet instantly. But the truly mind-bending part isn't the strength of these fields. It's what they do to the laws of physics themselves. In a magnetar's magnetic field, empty space itself becomes birefringent, splitting light into different polarizations like a cosmic prism. The magnetic field is so intense that it can actually change the shape of atoms, stretching them into needle-like structures that exist nowhere else in the universe. When a magnetar has what scientists euphemistically call a starquake, the results are apocalyptic. The neutron star's crust, locked to its magnetic field, suddenly shifts by mere millimeters. But those millimeters represent the movement of material denser than atomic nuclei across a surface area larger than most countries. The energy released in that instant is staggering. In 2004, a magnetar called SGR 180620, located 50,000 light-years away, had such a starquake. The burst of energy it released in 1/10 of a second was greater than all the energy our sun has produced in the last 100,000 years. The radiation from this event, despite traveling across half the galaxy, was so intense that it temporarily blinded several satellites and caused measurable changes in Earth's upper atmosphere. If this magnetar had been just 10 light-years away instead of 50,000, the radiation would have caused a mass extinction event on Earth. These aren't just impressive numbers, they're clues to something profound happening inside these objects. The magnetic fields of magnetars are generated by dynamo processes that we barely understand, involving the interaction of the neutron star's rotation, its superfluid interior, and exotic matter states that might not exist anywhere else in the universe. But here's where the mystery deepens into something almost philosophical. Recent observations have revealed neutron stars that are impossibly cold for their age. When neutron stars form, they're incredibly hot, with surface temperatures reaching tens of millions of degrees. Over time, they should cool according to well-established physical laws. We can predict exactly how hot a neutron star should be based on its age. Except some of them aren't following the rules. We've found neutron stars that are cooling far too rapidly, losing heat at rates that shouldn't be possible according to standard physics. The only way to explain this accelerated cooling is if something exotic is happening in their cores, something that provides an additional pathway for energy to escape. The leading candidates for this rapid cooling are processes involving particles that exist at the very edge of theoretical physics. Perhaps neutrons in the core are pairing up to form a superfluid, allowing heat to flow with zero resistance. Or maybe the extreme density is creating particles called hyperons, which contain strange quarks that fundamentally alter how energy moves through the star. Most intriguingly, this rapid cooling might be evidence of direct Urca processes, nuclear reactions that can only occur under the most extreme conditions imaginable. These processes would require the neutron star core to contain not just neutrons, but protons and electrons in specific proportions, creating a nuclear soup that exists nowhere else in the universe. But here's what's truly extraordinary. These cold neutron stars might be serving as cosmic laboratories for studying dark matter. Think about it. Neutron stars are incredibly dense gravitational wells that have been accumulating matter for millions or billions of years. If dark matter particles exist and occasionally interact with normal matter, they would inevitably fall into neutron stars and become trapped. Over cosmic time, a neutron star could accumulate significant amounts of dark matter in its core. When dark matter particles collide and annihilate, they release energy. This energy could provide the additional heating that prevents neutron stars from cooling as rapidly as we observe. Conversely, if we find neutron stars that are cooling exactly as predicted by standard physics, it would place strict limits on how dark matter behaves. This transforms every neutron star in the sky into a potential dark matter detector, each one a natural experiment that has been running for geological ages. We're essentially using the entire universe as our laboratory, with neutron stars as our instruments for probing the most mysterious substance in existence. The implications are staggering. If this theory is correct, studying neutron star temperatures could finally solve the dark matter mystery that has puzzled cosmologists for decades. We might discover that dark matter particles are actually much more interactive than we thought, or we might find evidence for entirely new physics that governs how matter behaves at quantum scales. But even as we contemplate these possibilities, nature keeps surprising us with discoveries that challenge our assumptions even further. In 2017, gravitational wave detectors picked up the signal of two neutron stars spiraling into each other across 130 million light-years of space. The collision that followed was unlike anything we had ever witnessed. When neutron stars collide, they don't just crash into each other like cosmic bumper cars. The collision is so violent that it tears apart the fabric of space-time itself, sending ripples through the universe at the speed of light. But what happened next was even more remarkable. The collision ejected clouds of neutron-rich material into space, material so dense that a handful would weigh as much as a mountain. In the intense heat and pressure of this cosmic catastrophe, something magical occurred. The ejected material began undergoing rapid neutron capture, a process where atomic nuclei grab neutrons faster than they can decay. This process, called R-process nucleosynthesis, created elements heavier than iron, including gold, platinum, and rare earth elements that are essential for modern technology. In that single collision, more gold was created than exists in all of Earth's oceans. The platinum in your car's catalytic converter, the gold in your jewelry, the rare earth elements in your smartphone, all of it was forged in the apocalyptic collision of neutron stars billions of years ago. We are literally made of stardust, but the most precious parts of us were made in the universe's most violent events. This discovery solved a decades-old mystery about where the heaviest elements come from, but it also raised new questions about neutron star interiors. The R-process nucleosynthesis we observed requires very specific conditions of temperature, density, and neutron flux. Understanding exactly how these conditions arise during neutron star mergers requires us to know what's happening inside these objects before they collide. The mystery deepens when we consider that we expected to detect many more of these kilonova events by now. Gravitational wave detectors have been scanning the skies for years, yet neutron star collisions seem to be much rarer than our models predicted. Where are all the missing kilonovae? Are neutron star binaries less common than we thought? Or do they take longer to merge than our calculations suggest? Each question we answer seems to reveal 10 more mysteries hiding beneath the surface. Neutron stars are not just exotic objects in distant space. They are windows into the fundamental nature of reality itself. They are testing grounds for physics beyond our current understanding, laboratories where matter is pushed to its absolute limits, and cosmic factories where the elements essential for life are created and distributed throughout the universe. As we peer deeper into this cosmic enigma, we encounter neutron stars that seem to exist in impossible states, challenging the very foundations of our understanding. Scientists recently discovered something that should make every physicist question everything they thought they knew about dense matter. 3 young neutron stars have been found with surface temperatures so cold they violate every theoretical model we've constructed. These aren't ancient, cooled-down remnants that have had billions of years to radiate away their heat. These are cosmic newborns, formed just thousands of years ago in the violent aftermath of supernova explosions. By every law of physics we understand, they should still be blazing hot, their surfaces glowing at temperatures of millions of degrees. Instead, they're sitting there in space like cosmic ice cubes, their temperatures far below what should be possible for objects their age. The implications are earth-shattering. The only way these neutron stars could cool this rapidly is if exotic physics is operating in their cores, physics that exists nowhere else in the known universe. We're talking about processes so alien to our experience that they might involve particles that haven't been seen since the first moments after the Big Bang. Think about what this means. These neutron stars are telling us that our understanding of how matter behaves under extreme conditions is fundamentally incomplete. There are entire realms of physics operating inside these objects that we haven't even begun to comprehend. It's like discovering that water can freeze at room temperature under certain conditions we never imagined possible. The leading explanation involves something called direct Urca cooling, a process so exotic it sounds like science fiction. In the crushing depths of a neutron star core, neutrons might be converting directly into protons and electrons, releasing neutrinos that carry away enormous amounts of energy. These ghostly particles, which barely interact with normal matter, could be streaming out of the neutron star's core at near light speed, carrying away heat faster than we ever thought possible. But here's where it gets even stranger. For direct Urca cooling to work, the neutron star's core must contain exactly the right mixture of neutrons, protons, and electrons. Too few protons, and the process can't occur. Too many, and the star would behave completely differently. The fact that we're seeing this rapid cooling suggests that neutron star cores exist in a precise knife-edge balance that we never predicted. This discovery is forcing us to confront an uncomfortable truth. We may know far less about the interior of neutron stars than we thought. Every model, every calculation, every theoretical framework we've built might be missing crucial pieces of the puzzle. We're like ancient astronomers trying to understand planetary motion without knowing about gravity. The mystery becomes even more perplexing when we consider what these cold neutron stars might be telling us about the fundamental structure of matter itself. At the densities found in neutron star cores, the normal rules that govern atomic structure completely break down. Neutrons, which we think of as elementary particles, might actually be falling apart into their constituent quarks. Imagine taking apart a watch and discovering that the gears inside are made of even smaller, more intricate mechanisms. That's what might be happening inside neutron stars. The neutrons that give these objects their name might be decomposing into a soup of quarks and gluons, creating a state of matter that existed only in the first microseconds after the Big Bang. This quark matter would behave unlike anything we've ever encountered. It might flow like a liquid with zero viscosity, conduct electricity with perfect efficiency, or exhibit properties that we haven't even imagined yet. The cooling rates we observe in these young neutron stars might be our first direct evidence that this exotic state of matter actually exists in nature. But the implications go far beyond just understanding neutron stars. If quark matter exists in neutron star cores, it means that nature has access to forms of matter that we've never been able to create or study in laboratory conditions. These objects become natural laboratories for exploring physics at energy scales that dwarf anything achievable with our most powerful particle accelerators. The Large Hadron Collider, humanity's most ambitious attempt to probe the fundamental nature of matter, can achieve energies of about 14 trillion electron volts. Impressive as that sounds, it's nothing compared to the energies locked inside a neutron star core, where the equivalent energies might be millions or billions of times higher. We're essentially using the entire universe as our particle physics laboratory. This realization has sparked a revolution in how we think about studying fundamental physics. Instead of building ever larger accelerators on Earth, we can turn our telescopes to the sky and observe natural experiments that have been running for millions of years. Every neutron star becomes a data point in our quest to understand the deepest laws of nature. But as we decode these cosmic messages, we keep discovering phenomena that stretch the boundaries of theoretical physics even further. Some neutron stars exhibit behaviors that seem to violate conservation laws that we thought were absolute. Others appear to exist in states that our most sophisticated models predict should be impossible. Consider the neutron stars that pulse with clockwork precision, their lighthouse beams sweeping across space with timing accuracy that rivals atomic clocks. Yet occasionally, these cosmic metronomes suddenly change their rhythm, speeding up or slowing down in ways that suggest their internal structure is far more dynamic than we ever imagined. These timing irregularities, called glitches, provide windows into the neutron star's hidden interior. The prevailing theory suggests that the neutron star's crust occasionally cracks under immense stress, like ice breaking on a frozen lake, but scaled up to cosmic proportions. When this happens, the star's moment of inertia changes, causing its rotation rate to shift. But here's what's truly mind-bending. The mathematics of these glitches suggests that neutron stars contain superfluid components that can flow without any friction whatsoever. Picture a liquid that, once set in motion, would continue flowing forever without slowing down. This superfluid might exist throughout the neutron star's interior, creating a complex system where different layers rotate at different speeds. The existence of superfluidity in neutron stars opens up possibilities that challenge our understanding of how matter behaves on cosmic scales. Superfluids can exhibit quantum mechanical properties on macroscopic scales, meaning that objects the size of cities might be governed by the same quantum laws that rule subatomic particles. This quantum behavior might explain some of the most puzzling observations we've made about neutron stars. Their magnetic fields might be supported by quantum vortices spinning through superfluid cores. Their rapid cooling might involve quantum phase transitions that occur nowhere else in the universe. Their ability to maintain structural integrity while spinning at impossible speeds might depend on quantum mechanical properties of matter that we're only beginning to understand. As these revelations pile up, we're forced to confront a humbling truth. Neutron stars are not just extreme objects in distant space. They are gateways to entirely new physics. They are testing the limits of every theory we've constructed about how the universe works. And they keep revealing that those limits are far more flexible than we ever imagined. The most profound mystery of neutron stars isn't just what they're made of or how they behave. It's what they're telling us about the nature of reality itself. These objects exist at the intersection of quantum mechanics, general relativity, nuclear physics, and thermodynamics, in regimes where all these theories must work together in ways we've never been able to test before. They're showing us that the universe is far stranger and more wonderful than we dared to imagine, filled with states of matter and energy that push against the very boundaries of what we thought was possible. And as our instruments become more sensitive and our theories more sophisticated, we're discovering that each answer we find opens doors to even deeper mysteries. The story of neutron stars is still being written, and the most exciting chapters are yet to come. As we stand on the threshold of new discoveries, we're beginning to realize that these cosmic enigmas might hold the keys to understanding not just the universe around us, but the fundamental laws that govern all of existence. The chase to unlock these mysteries has led us into uncharted scientific territory, where every new observation seems to contradict what we thought we understood. Just when we think we're getting closer to answers, neutron stars throw us another curveball that sends our theories spinning into chaos. Take the recent discovery that's left astronomers scratching their heads in bewilderment. We found neutron stars that are somehow accumulating dark matter in their cores, transforming these cosmic lighthouses into the universe's most sensitive dark matter detectors. Think about the sheer audacity of this concept. These objects have been sitting in space for millions of years, slowly collecting the most elusive substance in the universe like cosmic vacuum cleaners. Here's how this mind-bending process works. Dark matter particles, invisible and barely interacting with normal matter, occasionally collide with the dense neutrons inside these stars. When they do, They lose energy and become gravitationally trapped, sinking toward the neutron star's core like stones falling into a well. Over astronomical timescales, these particles accumulate in the star's center, building up concentrations of dark matter that exist nowhere else in the universe. But here's where things get absolutely wild. When dark matter particles finally meet their antimatter counterparts in the neutron star's core, they annihilate in bursts of pure energy. This process should heat up old, cold neutron stars in ways that we can actually detect with our telescopes. We're talking about using entire stars as dark matter laboratories, natural experiments that have been running since before Earth even existed. The implications are staggering. If this theory is correct, every cold neutron star we observe provides constraints on how dark matter behaves. Every temperature measurement becomes a clue in the greatest detective story in physics. We're essentially turning the entire universe into our experimental apparatus, with neutron stars serving as our instruments for probing the most mysterious component of reality. But even as we grapple with these revelations, neutron stars keep surprising us with behaviors that seem to mock our attempts at understanding. Consider the magnetars we discovered that periodically unleash bursts of energy so powerful they can be detected from across the galaxy. These aren't gentle stellar hiccups. These are cosmic temper tantrums that release more energy in milliseconds than our sun produces in centuries. What's causing these outbursts? The leading theory involves something called magnetic reconnection, where twisted magnetic field lines suddenly snap and reconfigure like cosmic rubber bands. But the mathematics of this process, when scaled up to magnetar strength fields, produces results that border on the impossible. We're dealing with magnetic fields so intense they could levitate a human being from the distance of the moon. Fields that literally warp the structure of empty space itself. These magnetic monsters are rewriting our understanding of electromagnetism on cosmic scales. In their vicinity, the normal rules of physics take a back seat to phenomena that exist nowhere else in the known universe. Light travels differently, space itself becomes polarized, and quantum mechanics operates in regimes that our textbooks never prepared us for. The mystery deepens when we realize that these magnetars might be connected to some of the most energetic events in the universe. Fast radio bursts, those split-second flashes of radio energy that outshine entire galaxies, might be originating from magnetars undergoing catastrophic magnetic field reconfigurations. If this connection is real, it means that neutron stars aren't just passive objects sitting in space, they're active participants in the most violent phenomena the cosmos has to offer. But perhaps the most unsettling discovery of all is how these objects seem to be connected to the fundamental structure of space-time itself. When neutron stars spiral into each other, they don't just create gravitational waves, they literally stretch and compress the fabric of reality. The ripples they generate carry information about the neutron star's internal structure, encoded in the precise pattern of space-time distortions. This discovery has opened up an entirely new field called gravitational wave astronomy, where we can peer inside neutron stars using the vibrations they create in space-time itself. It's like being able to see through solid walls by listening to the echoes of sound waves. Except we're using ripples in the very foundation of existence to probe the interior of objects 13 billion miles away. The precision of these measurements is almost incomprehensible. Gravitational wave detectors can measure changes in distance smaller than 1/10,000th the width of a proton. We're essentially listening to the universe's heartbeat, detecting the cosmic symphony created when the most extreme objects in existence dance their final dance before merging into something even more mysterious. Each gravitational wave signal carries a unique signature that tells us about the equation of state of neutron star matter. The way these objects deform as they spiral together depends critically on how stiff or soft their interior material is. By analyzing thousands of these cosmic collisions, We're building up a detailed map of how matter behaves under the most extreme conditions imaginable. But here's what's truly mind-bending about this process. The gravitational waves we detect were generated by events that happened millions or billions of years ago, when the universe was a very different place. We're essentially receiving messages from the deep past, cosmic postcards that have been traveling through space for longer than complex life has existed on Earth. These ancient signals are teaching us that neutron stars have been shaping the evolution of the universe in ways we never suspected. Every collision has been seeding space with heavy elements. Every merger has been stirring the cosmic pot of chemical evolution. The gold in ancient meteorites, the platinum in billion-year-old rock formations, all of it bears the signature of neutron star collisions that happened in the distant past. This realization has fundamentally changed how we think about our place in the cosmos. We're not just observers of the universe, we're products of it. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in the nuclear furnaces of stars and scattered by the violent collisions of neutron stars. We are literally made of neutron star debris, cosmic dust that has been processed through the most extreme physics laboratories in the universe. But as we trace our elemental heritage back to these cosmic catastrophes, we keep discovering that the story is far more complex than we ever imagined. Recent observations have revealed that not all neutron star mergers produce the same mix of heavy elements. Some collisions seem to favor the production of certain isotopes over others, suggesting that the internal structure of neutron stars varies in ways that fundamentally affect the chemistry of the universe. This discovery has profound implications for understanding how chemical complexity arose in the cosmos. The elements that make life possible weren't just randomly scattered through space, they were carefully crafted in the cores of neutron stars and distributed according to patterns that we're only beginning to decipher. Each merger was like a cosmic chemistry experiment, mixing and matching nuclear ingredients to create the periodic table of elements that forms the foundation of all matter. The precision required for this process is absolutely staggering. The conditions inside merging neutron stars must be tuned to just the right temperature, density, and neutron flux to produce the mix of elements we observe in the universe today. A slight change in any of these parameters would result in a cosmos with completely different chemistry, possibly one where complex molecules, planets, and life could never form. This fine-tuning raises profound questions about the nature of reality itself. Are the laws of physics somehow calibrated to produce neutron stars with exactly the right properties to create a universe suitable for complexity and life? Or is our universe just one of countless possibilities, selected by the anthropic principle because we happen to exist within it, to observe it? The answer to these questions might lie hidden in the deepest mystery of neutron stars themselves. As we've seen, these objects exist at the intersection of all the fundamental forces of nature. They're governed by gravity, electromagnetism, and nuclear forces, all operating simultaneously in regimes where our current theories begin to break down. Understanding how these forces work together in neutron star interiors might reveal new principles that govern the structure of reality itself. Some theorists believe that neutron stars might be windows into extra dimensions, spaces beyond the 3 dimensions of length, width, and height that we experience in everyday life. The extreme curvature of space-time around these objects might allow particles or forces to leak into our universe from these hidden dimensions, creating phenomena that we observe as anomalous cooling, unusual magnetic fields, or unexpected equation of state properties. Other scientists think that neutron stars might be natural laboratories for studying quantum gravity, the long-sought theory that would unite quantum mechanics with general relativity. The conditions inside these objects might be extreme enough to reveal quantum effects operating on macroscopic scales, showing us how the universe behaves when the smallest and largest scales of physics merge into a single unified description of reality. As these possibilities swirl around us, we're faced with the humbling realization that neutron stars might be teaching us that the universe is far stranger and more wonderful than we ever dared to imagine. These objects are not just exotic curiosities in distant space. They are fundamental components of reality itself, cosmic laboratories where the deepest laws of nature are constantly being tested and refined. The story of neutron stars is really the story of our quest to understand the universe at its most fundamental level. Each discovery brings us closer to answering the most profound questions about existence. What is matter? How does the universe work? What are the limits of physical possibility? And perhaps, most importantly, what does it all mean for our understanding of our place in the cosmic order? As we stand on the threshold of even greater discoveries, with more sensitive gravitational wave detectors coming online and more powerful telescopes being built, we're preparing to peer even deeper into these cosmic enigmas. The next decade promises to be a golden age of neutron star astronomy, where we might finally solve mysteries that have puzzled humanity for generations. But if history has taught us anything, it's that each answer we find will only reveal deeper questions, more profound mysteries, and more exotic possibilities than we ever imagined. The universe seems to delight in keeping us humble, constantly reminding us that reality is always stranger, more beautiful, and more mysterious than our theories predict. The deepest mystery of neutron stars isn't just about these objects themselves. It's about what they reveal about the fundamental nature of existence. They are cosmic mirrors that reflect back to us the deepest truths about reality, challenging us to expand our understanding and embrace the magnificent complexity of the universe we inhabit. And as we continue this journey of discovery, we're beginning to realize that the greatest mystery of all might be that there are always more mysteries waiting to be uncovered. The story takes an even more twisted turn when we consider what happens during the final moments before neutron star collisions. As these cosmic titans spiral toward each other, something extraordinary occurs that challenges everything we thought we knew about the behavior of matter under extreme stress. The neutron stars begin to deform, stretching and bulging like cosmic taffy being pulled apart by invisible hands. This deformation process, called tidal disruption, reveals secrets about neutron star interiors that we could never access any other way. The stiffer the neutron star material, the less it deforms. The softer the interior, the more dramatically it stretches. By measuring these deformations through gravitational wave signals, we're essentially performing cosmic stress tests on matter compressed beyond anything we can imagine. But here's where things get absolutely mind-bending. Some neutron stars seem to resist deformation in ways that suggest their interiors are more rigid than diamond, yet somehow maintain the fluidity needed for the complex internal processes we observe. It's like discovering a material that's simultaneously harder than steel and more flowing than water, existing in a state that defies our basic understanding of how matter should behave. This paradox has led some physicists to propose that neutron star cores might contain phases of matter that transition between different states depending on the external conditions. Picture a substance that acts like a solid when squeezed gently, but becomes a superfluid when compressed beyond a certain threshold. These phase transitions could happen instantaneously throughout the neutron star's interior, creating a dynamic, ever-changing internal structure that responds to gravitational stresses in ways we never predicted. The implications of this discovery reach far beyond neutron star physics. If matter can exist in these exotic transitional states, it might explain phenomena we observe throughout the universe. Dark matter itself might be composed of particles that exist in similar phase transitional states, flickering between different forms of existence in ways that make them nearly impossible to detect directly. Even more intriguingly, these phase transitions might be connected to the fundamental structure of space-time itself. Some theoretical physicists propose that space and time are not continuous fabrics, but are instead made up of discrete units that can transition between different configurations. The extreme conditions inside neutron stars might be revealing the granular nature of reality itself, showing us that the smooth space-time we experience is actually composed of countless tiny pixels of existence. This brings us to one of the most shocking discoveries in recent neutron star research. Scientists have found evidence that some neutron stars might contain microscopic black holes in their cores. These aren't the stellar mass black holes we're familiar with, but primordial black holes that could have formed in the earliest moments of the universe and somehow become embedded within neutron star matter. The existence of such objects would revolutionize our understanding of both black hole physics and neutron star structure. These microscopic black holes would slowly consume the neutron star from within, growing larger and more massive over cosmic time. The process would be incredibly slow, taking billions of years to have any noticeable effect, but it would fundamentally alter how we think about the long-term evolution of these objects. What makes this possibility even more extraordinary is that it might explain some of the anomalous cooling rates we observe in certain neutron stars. As matter falls into these microscopic black holes, it would release energy through Hawking radiation, creating a heat source deep within the neutron star core. This internal heating could counteract the normal cooling processes, leading to temperature profiles that don't match our standard models. But the implications go deeper still. If neutron stars can harbor microscopic black holes, it suggests that the boundary between different types of compact objects is far more fluid than we imagined. We might be looking at a spectrum of exotic objects that blur the lines between neutron stars, black holes, and possibly entirely new categories of cosmic entities that we haven't even named yet. This realization has sparked intense debate about the nature of gravitational collapse itself. When massive stars collapse, do they always form clean categories of objects like neutron stars or black holes? Or might the collapse process sometimes create hybrid objects that combine characteristics of both? The answer could fundamentally change how we classify and understand the most extreme objects in the universe. Recent observations have provided tantalizing hints that such hybrid objects might actually exist. Astronomers have discovered compact objects with masses that fall in the mysterious gap between the heaviest neutron stars and the lightest black holes. These objects shouldn't exist according to our current theories, yet there they are, challenging us to expand our understanding of what's possible in the universe. Some of these mysterious objects pulse like neutron stars but have masses that should force them to collapse into black holes. Others seem to have the mass signatures of black holes but exhibit behaviors that suggest they have solid surfaces. We're dealing with objects that seem to exist in quantum superposition states on cosmic scales, simultaneously being one thing and another until we observe them closely enough to collapse their wave function. This quantum mechanical behavior on astronomical scales opens up possibilities that stretch the imagination. If neutron stars can exist in superposition states, maintaining multiple configurations simultaneously, it might explain why they seem to violate so many of our theoretical predictions. We might not be observing single, definite objects, but rather probability clouds of different possible neutron star configurations. The mathematics of this possibility lead to some truly bizarre predictions. Neutron stars might be able to tunnel between different internal configurations, switching from one equation of state to another through quantum mechanical processes. They might be able to exist in multiple spin states simultaneously, appearing to rotate at different rates depending on how we observe them. They might even be able to occupy multiple locations in space at the same time, creating interference patterns in their gravitational wave emissions. These aren't just theoretical curiosities. They're potentially observable phenomena that could revolutionize our understanding of how quantum mechanics operates on cosmic scales. If we can detect quantum superposition in neutron star properties, it would provide the first direct evidence that the strange rules of quantum mechanics apply to objects as massive as entire stars. The search for these quantum effects in neutron star observations has become one of the most exciting frontiers in astrophysics. Scientists are developing new analysis techniques that can detect subtle correlations and interference patterns in neutron star signals that might reveal their quantum nature. The discovery of macroscopic quantum behavior in these objects would rank among the greatest scientific breakthroughs in history. But as we push deeper into these quantum mysteries, we encounter phenomena that challenge the very foundations of our understanding of reality. Some neutron stars seem to exhibit behavior that suggests they're communicating with each other across vast distances, coordinating their activities in ways that would require faster-than-light information transfer. This apparent violation of relativity has led to speculation about quantum entanglement operating on galactic scales. The idea sounds absurd, but the observational evidence is becoming harder to ignore. Binary neutron star systems sometimes exhibit synchronized behaviors that can't be explained by gravitational interactions alone. Their magnetic fields seem to align in ways that suggest some form of instantaneous communication. Their timing glitches sometimes occur simultaneously across multiple systems, as if they're responding to some cosmic signal that we can't detect. If neutron stars are indeed quantum entangled across cosmic distances, it would suggest that the universe operates on principles far stranger than we ever imagined. It would mean that information can travel instantaneously across the cosmos, that distant objects can influence each other without any apparent mechanism, and that the fabric of reality itself might be fundamentally non-local in ways that Einstein never dreamed of. This possibility has led some theorists to propose that neutron stars might be components in a vast cosmic quantum computer, processing information about the universe's structure and evolution in ways that we're only beginning to glimpse. Each neutron star would be like a quantum bit in this cosmic processor, storing and manipulating information about the fundamental nature of reality itself. The implications of such a system would be staggering. It would suggest that the universe is not just a collection of objects moving through space, but a vast information processing system that computes its own future evolution. Consciousness itself might emerge naturally from this cosmic computation, making awareness not an accidental byproduct of evolution, but a fundamental feature of reality that was built into the universe from the very beginning. As we contemplate these mind-bending possibilities, we're forced to confront the humbling realization that neutron stars might be showing us that reality operates on principles so alien to our everyday experience that we lack the conceptual framework to fully understand them. We're like ancient philosophers trying to understand the nature of fire without knowing about atoms, electrons, or chemical reactions. The deepest mystery of neutron stars isn't just what they're made of or how they behave. It's what they reveal about the fundamental nature of existence itself. They are cosmic laboratories where the universe experiments with the limits of physical possibility, testing the boundaries between matter and energy, between space and time, between the quantum and the classical, between the possible and the impossible. Each new discovery brings us face to face with phenomena that stretch our understanding to its breaking point. We find objects that shouldn't exist, behaviors that violate our theories, and connections that challenge our basic assumptions about how reality works. Yet somehow these discoveries don't break our understanding, they expand it, revealing new dimensions of possibility that we never knew existed. The story of neutron stars is ultimately the story of human curiosity confronting the infinite mystery of existence. These objects serve as cosmic mirrors that reflect back to us the deepest truths about reality, challenging us to grow, to question our assumptions, and to embrace the magnificent uncertainty that lies at the heart of all scientific discovery. As we stand on the threshold of even greater revelations, with new instruments coming online that will probe these mysteries with unprecedented precision, we're preparing to enter a new age of discovery. The answers we find will likely be stranger and more wonderful than anything we can currently imagine, opening doors to new universes of possibility that will reshape our understanding of what it means to exist in this cosmos. But perhaps the most profound mystery of all is why the universe chose to create these objects in the first place. In a cosmos that could have evolved in countless different ways, why did nature select a path that leads to neutron stars, objects so extreme that they push the very laws of physics to their breaking points? The answer might reveal something fundamental about the nature of existence itself, something that connects the smallest quantum fluctuations to the largest structures in space, something that bridges the gap between mind and matter, between consciousness and cosmos. The deepest mystery of neutron stars is that they exist at all, and that we exist to wonder about them. In the grand symphony of cosmic evolution, these objects play notes so complex and beautiful that they hint at harmonies we're only beginning to hear. As we listen more carefully to their cosmic song, we're discovering that the universe is not just stranger than we imagine, it's stranger than we can imagine. And that might be the most wonderful mystery of all. The journey into neutron star mysteries takes an even more bewildering turn when we examine what happens during the split seconds of their formation. Picture the moment when a massive star's core collapses. We're talking about an event so violent that it compresses matter equivalent to our entire sun into a sphere smaller than Manhattan, in less time than it takes light to travel from Earth to the moon. But here's what absolutely defies comprehension. During this collapse, something extraordinary happens to time itself. The intense gravitational field creates what physicists call extreme time dilation, where time literally slows down near the neutron star's surface. If you could somehow survive standing on a newly formed neutron star, you'd watch the rest of the universe speed up around you like a cosmic fast-forward button had been pressed. This isn't science fiction. This is Einstein's general relativity pushed to its absolute limits. The gravitational field is so intense that light climbing out of the neutron star's gravity loses energy, becoming redshifted to longer wavelengths. What appears as blue light on the neutron star's surface would look red to us, observing from a safe distance. The neutron star is literally stretching the fabric of space-time around it, like a bowling ball placed on a trampoline. Yet somehow, within this warped reality, nuclear processes continue operating with clockwork precision. The neutron star's core maintains nuclear reactions that follow quantum mechanical rules, even as space-time itself is being twisted into pretzels around them. We're witnessing the marriage of Einstein's relativity with quantum mechanics in the most extreme natural laboratory imaginable. This brings us face to face with one of the most profound puzzles in modern physics. Inside neutron star cores, we believe that nuclear matter exists in a state called nuclear pasta. No, this isn't some cosmic Italian cuisine. It's matter arranged in shapes that resemble different types of pasta. As density increases toward the core, nuclear matter first forms gnocchi-like spheres, then transitions to rod-shaped structures like spaghetti, then flattens into lasagna sheets, before finally creating tube-like structures resembling rigatoni. The physics behind nuclear pasta challenges everything we thought we knew about how matter organizes itself under pressure. These aren't random arrangements. They represent the most energy-efficient ways for nuclear matter to pack together at different densities. The transition between these phases might be what determines many of the exotic properties we observe in neutron stars. But here's where the mystery becomes almost philosophical. The nuclear pasta phases exist in a realm where the distinction between individual particles breaks down completely. Protons and neutrons lose their individual identities and merge into collective quantum states that span the entire neutron star. We're dealing with objects where quantum mechanics operates on scales larger than entire cities. This quantum coherence on macroscopic scales opens up possibilities that seem to violate our intuitive understanding of how the world works. The entire neutron star might function as a single, giant quantum object, with properties that emerge from the collective behavior of quintillions of particles acting in perfect unison. It's like discovering that an entire metropolitan area could behave as a single atom. Recent theoretical work suggests that this macroscopic quantum behavior might explain some of the most puzzling neutron star phenomena. The precision of pulsar timing, the stability of ultra-fast rotation, and the strength of magnetar magnetic fields might all emerge from quantum mechanical effects, scaled up to astronomical proportions. Consider what this means for our understanding of the universe. We've always assumed that quantum mechanics was relevant only at microscopic scales, while classical physics governed the motion of planets and stars. Neutron stars are showing us that this division might be artificial, that quantum effects can dominate the behavior of objects containing more matter than our entire solar system. This realization has sparked a revolution in theoretical physics. Scientists are developing new mathematical frameworks that can describe quantum mechanics operating on cosmic scales. They're discovering that many of the strange properties of quantum mechanics, superposition, entanglement, tunneling, might be fundamental features of reality at all scales, not just exotic curiosities confined to laboratory experiments. The implications stretch far beyond neutron stars themselves. If macroscopic quantum mechanics is real, it might explain mysteries that have puzzled astronomers for decades. Dark matter might consist of particles that exist in quantum superposition states, flickering between different forms of existence. Dark energy might be the result of quantum fluctuations in the vacuum of space, scaled up to affect the expansion of the entire universe. Some researchers are even exploring whether consciousness itself might be a macroscopic quantum phenomenon. If neutron stars can maintain quantum coherence across their entire structure, perhaps the human brain, with its network of interconnected neurons, might also function as a quantum system. This could provide a scientific basis for understanding how consciousness emerges from the complex interactions of matter and energy. From sugar cubes that weigh as much as humanity to cosmic lighthouses spinning faster than industrial drills, neutron stars have revealed themselves to be far more than just exotic objects in distant space. They are windows into the deepest mysteries of existence itself, challenging everything we thought we knew about matter, energy, space, and time. As we've journeyed through their impossible physics, we've discovered objects that shouldn't exist according to our theories. Yet there they are, spinning away in defiance of our understanding. The answers they're providing are rewriting the textbooks of physics and opening doors to possibilities we never dared imagine. The deepest mystery isn't just what lies inside these cosmic enigmas, it's what they're telling us about the fundamental nature of reality itself.